MCQ based questions first. So this is your question that says that the final products of normalizing and quenching of a eutectoide steel are dash and dash respectively. So you have to tell, if you go for these type of heat treatments, what is the kind of microstructure that you can attain. So the options are perlite and bainite, martensite and fine perlite, bainite and coarse perlite. Fine perlite and martensite. So you have to say which of the following option is right. So can anybody try to attempt this question? So basically we are talking about two types of heat treatments, and these heat treatments are based on, for example, you have seen your CCT and TTT diagrams. So for example, when you have a diagrams where you have a transformation in a steel, so you have some this kind of a diagram, say for example, and then you have this C-type curve for your transformation. So normally this is your transformation curve, and you can choose your cooling rate. So what is normalizing? Normalizing is the cooling when you are cooling it in instead of furnace, you are cooling it in an air. So what happens by that? You are able to uh, have a faster cooling rates as compared to your furnace cool. So for example, you will have something cooling rate like this, right? It will pass like this, normalizing. While for quenching, you have a very fast cooling rates, which are so fast because of your utilizing water as a medium. So you have something like this. Okay, so you have two different structures. You understand that in quenching, you are trying to bypass other microstructures such as perlite or bainite, right? Instead, what you are getting a martensite because of your fast cooling rate. So even quenching, the right option will be martensite. And for normalizing, your option is fine perlite, right? Because you are not doing for a if you would have gone for furnace cooling, you could have found perlite, but that perlite would have been your coarser perlite, right? So normalizing mostly gives you perlite and martensite, right? Is the option for your quenching. So the next question says, in a medium carbon steel, martensite will be produced during furnace cooling. So you have to say, is it true or false? Can anybody answer this?
False, right? It won't be furnace cooling will be slow, yeah.
Okay, so first we have to know what is medium carbon steel. Do you know what is a medium carbon steel? When you have less than around say 0.26, it is a low carbon steel, but if it is around 0.25 to 0.6, uh, it is around 0.25 to 0.6, it is around medium carbon steel. So we are talking about these types of steels. So it is saying that in a medium carbon steel, martensite will be produced during furnace cooling. So first thing is that in your martensite will always be formed when you are having a faster cooling rate. The furnace cooling is a very slow cooling rate, so the martensite will not be found. Second, because if you have a medium carbon steel, you have a, if it is a equilibrium cooling and not a non-equilibrium cooling, then you will have the formation of, generally in a medium carbon steel, there are two phases that you can find. One is alpha pro-eutectic and your superlight, right? So this is your equilibrium phases. So you should know what are the equilibrium phases. While the martensite, which is given in this will not be formed because it is a furnace cooling, right? So next question says that the steel containing more than 0.8% carbon are called dash, and cast iron containing less than 4% carbon are called dash. So you should, for these questions, you should have an idea about your iron carbon diagram. So you uh, have seen there are different invariant points in your iron carbon diagram, and those invariant points include eutectic point, eutectoid point, peritectic point. So here you have 2 points, and you should know where exactly these points lie in the iron carbon diagram, right? For example, you know the eutectoid point where you have a gamma transition, gamma phase with your perlite phase, austenite phase with your perlite phase. So you know this is your, say for example, first we'll do for one. So this is your gamma, which is austenite, and then you have here alpha plus, say for example I'll write cementite, right? And this is your alpha, this is your alpha plus gamma, right? So this is your eutectoid point because we have a gamma transition to alpha plus this cementite, right? So you have to tell what is the point. If it is more than 0.8% carbon, obviously you know your eutectoid point, it lies around 0.76 percentage. This is a 0.76 percentage carbon, but it is greater than 0.76, so it is 0.8%, right? It is somewhere here in this region, which is actually gamma plus cementite. So you have to tell what is it called. Is it hypoeutectic, hypoeutectoid, hypereutectoid, or hypereutectic?
0.76 is eutectoid, right? Not
What?
eutectic. 0.76% carbon is eutectoid point, right? Not
Okay.
eutectic. Yeah.
No, no, it is eutectoid point. So I'm asking
Okay.
what is the right answer? It is greater than 0.8, so it is above your eutectoid point. So it is in
Yeah.
a hypereutectoid zone.
Hypereutectoid. Yeah.
So the hypereutectoid is here, and this is your hypereutectoid, right?
Yeah. Yeah.
Now you have to see what is for the other point, which is less than 4% carbon. This is usually seen for your cast iron. You know, if you have a greater than this percentage carbon, so you have a one point which is called as uh, eutectic point. So you know where in your iron carbon diagram where lies the eutectic point. You should know where your eutectic, eutectoid points lie, then only you can understand these diagrams. So if you have seen a eutectoid point at 0.76%, what is your eutectic point? At what percentage carbon?
Around 4.4%.
Yes, it is around 4.4%. So this is 4%. So that means it is less than your eutectic composition. The carbon percentage is less than your eutectic composition. So when it is less than your eutectic, then you will call it as hypoeutectic, right? And it is not a eutectoid. Why? Because at this region, when you have a iron carbon diagram, at eutectic point, which is 4 point around 4.46, so you have a phase of liquid in equilibrium with your alpha plus cementite, for example. So this is your eutectic point. So that is why option C will be right, not option B. Okay. Then we have another question that says, in which of the following medium is the cooling done during annealing? Air, furnace, water, or oil? So you have different mediums to cool the material, right? For example, you have air. You can normally what is done in annealing, you take your sample, you put it in a furnace at a certain temperature, which is above your A3 temperature. See, this is your A1 temperature. This is your A3 temperature where you have a gamma transformation. So about this A3 temperature, you take your sample, you keep the furnace at greater than A3 temperature, and then you hold it for some time. What is your treatment? And then you take out your sample, and then there are different options that you can do. If you can let it to cool in the furnace, then it is called annealing. But if you, this is the right option for this because it is for annealing. But if you are allowing it to cool it in air, what is it called? Generally, when you take your sample from the furnace and you let it cool in the air, what is it called? The treatment is called
Normalizing.
Right, because you have a slightly faster uh, cooling rates in normalizing. In annealing, you have a very slow rate, right? So this is normalizing, and in furnace it is annealing. While if you are in water or oil medium you are using for cooling, then you can call it as quenching, right? Usually, oil will have in between water and oil. Water is having a much faster cooling rate as compared to oil. It depends on their specific capacity, like specific heat capacity, how much heat they can retain, right? So quenching for these type of processes, right? So these are different types of heat treatments that are possible because of your different cooling rates. Okay. Then we have another question which says which of the followings are not correct. That means it is saying that you are doing annealing and it is a slow cooling and it will result in the formation of force per light. So it is a relationship between your heat treatment, type of heat treatment, like if it is slow, fast, or what it is, and the type of microstructure you are being formed. So you have to say annealing is a slow cooling and results in cores per light. Normalizing is a slow cooling and results in cores per light. Normalizing is a fast cooling and results in fine per light. Annealing results in which is a fast cooling results in fine per light. So you have different combinations. For this, you will require two things. One is what are these. First, you have to see these two relations, right? Which is a slow cooling, which is a fast cooling, and then you have to relate it to their microstructure. So you can try to answer this question. Anybody wants to attempt it?
And
Anybody
the
wants?
correct answer, yeah,
Yes.
B and D.
Okay, so B and D. So you are saying this option B, and you are saying D. Okay. So, so for example, I'm saying if you are doing first we know that normalizing is a slow cooling as compared to annealing. Annealing is a comparatively a faster cooling. So these options are right for this. And now how do we understand which type of a structure will be formed? That we determine from our TTT diagram, it is the transformation diagram. So you understand that when you have such type of a structure, if you have a very fast cooling rate, so if you have a very fast cooling rate, such as for example this, right? So you are having a faster cooling rates, while if you have a very slower cooling rate, such as like this. So there are two types of structures that can be formed. Here you have a coarser perlite, and then you have a finer perlite, and below that you always have a coarser benite, and then finer benite. Always when you have a higher cooling rates, you have a smaller structure, finer structure. So based on this, it tells that if you go for annealing, you will always have a coarser perlite instead of a fine perlite. Okay. While if you go for normalizing, this is annealing and this is your normalizing. So for normalizing, you will have a fine perlite, right? So a combination of what kind of heat treatment you are doing and what is its relation to your rate of heat and the type of microstructure will be determined by your TTT diagram. Okay. Next question says that in a stress strain diagram, the maximum stress below which a body retains its original dimensions when the load is removed is known as ultimate tensile stress, fracture stress, yield stress, or true stress. So you understand the stress strain curve. Stress strain curve is nothing but it is a relationship between how much strain, like a function of your strain, how much strain you are giving to a material and how much it is deformed. Okay. So based on your how much for load you are giving to the material. So for example, if you have something like this, you normally have a stress strain curve like this. So it says that the maximum stress below which the body retains its original dimensions. So these original dimensions are maintained only up to your certain point, and that point is referred to what? Is it ultimate tensile stress, fracture, yield, or true stress?
Yield stress, right?
Yes, it is yield stress. Up to yield stress, your material will behave as if it is elastically deforming, and that once the removal of the load, it will come back to its original position. But this is also known up to a elastic limit, like the limit up to which you have a elastic deformation occurring in your material. But beyond that, you will have a plastic deformation, and that deformation will cover your ultimate tensile stress. Comes in your plastic deformation. This stress also comes in your plastic deformation, while as your yield stress comes in your elastic deformation. Okay, so yield stress is the right option. Okay, then we have another question that says, this is a question that is based on same principle, which is stress strain curve. So it says that 10 kg of load produces an extension of 4 mm in a wire. So this is your material, and it is producing some extension. So that means it is a elongated some by some length, which is delta L. Okay, and you are giving a load of 10 kg. So you are given a weight, and it's saying the length and the diameter of the wire is 10 meters and 2 mm respectively. So you are given a wire and its dimensions. So if it is a wire like this, so you have length of 10 meter and you have a dia of 2 mm, right? So calculate the Young's modulus of wire in pascals. So you have to calculate it. So how will you do that? You will use your stress strain relationship, which says that your stress is proportional to your strain, and you use a constant of Young's modulus. So everything is given. What you have to find, this E. So this E will be actually a function of your stress, whatever you are using, and your strain. So your stress is given by force per unit area always, right? This is the value of your sigma, while for your delta, this strain, we will refer it to the change in length because we are having an elongation. It's a tensile test with respect to its length. So we will have some formula like this. So you just have to put the values. So force, we do not know the force here, but because we know the weight, so you know force is equal to R m into A, m into G here. So your mass, you know 10 kg. You can take the value of G, say for example 10 or 9.8. Okay, can write meter per second square. Okay, so now you can write your force value, which is your P. So you can write it here, 10 multiplied by 10, and you have to write your area. So what will be the area here? The area is actually, because it is this sample, so this area is exposed on your load, right? The load is put on this area. So this is your area. This is 2 mm. The diameter of this is 2 mm. So the circular area is your diameter. Sorry, is your area. So you can take area as a area of your circular surface. So it will be pi by 4 d square. D is here 2 mm. So you uh, use, because we are calculating all in our standard units, so we can write 2 multiplied by 10 to the power of 3 minus 3. So that would be your area, pi d square. So that will be square, and then we will have length. The total length is 10 meters, and you have to tell what is the deformation. That is 4 mm. So that would be 4 multiplied by 10 to the power minus 3. So you have to tell what is the answer. Now you just have to put in the values. You have to give your answer in, okay, Pascal, so right. That is fine. So you should know what is the unit of Pascal is nothing but it is Newton per meter square. Okay. Now you have to just put the value and tell the answer. So can anybody tell what is the right answer?
Madam C, 7.9 into 10 is to power 9.
7.9 multiply. Yes, this is the right answer. So you have Young's modulus of 7.9 into 10 to the power 9. Okay. Okay. So now we can move to next question. A stress strain curve is shown for two materials A and B. If the modulus of elasticity for the material A and B are EA and EB, so you are given two modulus of elasticity, nothing but Young's modulus, then what will be the correct option? Which of the following is right? So, which of the following will have a higher or equal to, what is the relationship between your Young's modulus? So, you have to say based on your diagram. So, what would be the right option? Which one will have, what is the right relationship? Any options for this?
Option C.
Okay, option C. So why we have option C? Because you understand that if you have a one curve which is given by A, so for example we are talking about a constant strain because we have to see. So this is our constant strain curve. Okay, so we say that for A you have a yield, it yields at this point, while as for B, or no, we can say for a constant stress like this. It will be better to do that. So we can say that which of the following will yield first. So it is A which will yield first because the strain that it is undergoing is this much. We can say S1, while for a B it is going to a larger strain. So because it is having a smaller strain and the largest value of yield, so it will yield first and then this will yield second. Okay. So just based on your elastic deformation curves, you can determine which one will yield first and which will yield after that. So we have another question that says, in a tensile test on a mild steel sample, the ultimate tensile stress as compared to fracture stress is less, more, or same. So you know what is ultimate tensile stress in a stress strain curve. You also know what is a fracture stress. So you have to say if it is a mild steel sample. It is important to mention what kind of a sample it is. So if it is a mild steel sample, the what will be the value of your stresses?
It's B, right?
The ultimate tensile stress will be more, right? Why? Because once it undergoes a fracture, the stresses are released, and those stress release causes a decrease in your fracture. So this is your fracture point, while your ultimate is somewhere here. So this is your ultimate tensile stress, while this is your fracture stress. So always whenever you have a material, it goes elastic deformation up to a certain point, then after that it starts going plastic deformation and reaches a maximum value which is known as ultimate tensile stress. And then if you increase further the strain, the material will undergo fracture, and that fracture will result in a release of your stresses, and so you have a lower stress. So always your ultimate tensile stress will be higher as compared to your fracture stress. So you have to remember this. Okay, now we have another question that says, suppose applied load is P, okay, and the radius of your rod is 4 times after the application of the load. Okay, new Young's modulus will be, if original Young's modulus is E. So you have to say what is the right option for this. So you are doing some variation in your radius of your rod. So do you think the effect on your Young's modulus will be E 2 E by 3, E by 2 or E by 4? What will happen to your Young's modulus?
I think it should remain same
Right, why?
because E is the property of the material.
Right, E is always a property of the material and it will not change during your, for example, tensile testing. It will remain constant. So the right option will be E. So you should remember that there is no change in your Young's modulus during the testing of your ultimate testing. So it is material property and does not depend on your applied stresses, and like it does not depend on how much you change your dimensions of the material. Okay. Then we have another question that says if the length of the rod is L, the area of cross section is A, and the modulus of elasticity is E, then the increase in length of the rod due to tensile load P will be. So this is the same question which is based on your stress strain curve. So you have to use your stress equation which is given by stress strain equation which is given by this. So you have to say if the length of the rod is given and the area of the cross section is given and you are given a modulus of elasticity, then you have to say what will be the increase in length. So you have to find what is delta L. Using you just have to rearrange. So how will we do it? We just put the actual value. So we will have force P by A here because we have to retain our delta L here. So we will retain our delta L here. So we will multiply it with our length and divide it by with our E, right? So what is the right option?
C.
C. Okay. So next we have a question which says a bar of 80 mm cross 80 mm square cross section is subjected to a tensile load is elongated up to 1.95 mm if the length of the bar is 5 meters and your E is 200 GPa. Find out the amount of load through which a bar is subjected to. So you have to find the load which is on the bar. So firstly it is a square bar. So you have to say you have something this kind of an area where you have this is 80 and this is your 80. So this is your surface that is subjected to load. So you have surfaces. Remember this is in mm because we have to change the values. Okay, and then we are given that it is elongated up to 1.9. So you are given delta L also. So that is 1.95 mm. Okay. If the length of the bar is 5, so you are given L, which is 5 meters, and you are given E, which is your Young's modulus, which is 200 GPa. So can you find the load just using your stress strain equation again? So this is your equation. So you have to put down your values. So it will be something 200. If you, okay, 200 multiplied by 10 to the power 9 multiplied by your strain, that will be 1.95 divided by your 5. So because we have units in same, so this will be 10 to the power minus 3 and you have to multiply it by area. So because it is a square, so area will be the square of your sides. So it will be 80 cross 80 multiplied by 10 to the power minus 6. So what is the answer? Final answer for your load? So have you any answer?
500 kilonewton.
500 kilonewton. So option C. Okay, that is your right answer. Okay. Next question is that a rod of 40 dia is subjected to an axial tensile of 40 kilonewton. So you are given this time the diameter of your rod. So this is your rod. So I'm sorry for the. So you have to again use the same equation. You can write this question. So you have a rod. It is having a dia of 40 axial tensile load of 40 kilonewton. So it has 40 kilonewton. If the length of the bar is 3 meters, so this is 3 meters. And your E is 200 GPa. So your E is also given. Your load is given, which is your SA load. So your E is also given, which is 200. And you have to find delta G, so delta L, sorry. Again, using the same equation where we have force per unit area equal to our elongation, and your delta L will has to be calculated, and your total length, you know the total length is 3 meters, right? 3 meters. So you have to just find your delta L. That will be equal to your force, that is 40 kilonewtons. So 40 multiplied by 10 to the power 3 divided by the area. What would be the area in this case? Because it is a rod, so we will have a circular surface that will be subjecting to tensile load. So we will have pi by 4 of area. So it is 40. So because we have to convert it into meters, so 10 to the power minus 3 square, that is your P by A. You have to multiply it by your length, that is 3, and you have to divide it by your E, which is 200 into 10 to the power minus 6, minus 9, or 9, sorry. Oh, 9, minus. So now you have delta L. So can you calculate what is the value of delta L? Any answers? So since we are trying to, so the answer that you will get is in meter, I think, because we have done the conversions. So you find the answer. So has anybody solved it? Have you tried to solve it? Because you just have to put the values. Just have to tell how much the elongation will be there. And if you have not tried to solve it, you just have to put the values. So I think the right answer is 0.477 mm. So this is your right answer if you have tried to solve it. Should we move to the next question?
Yeah, madam.
So we have this question that says match the correct answer from group B for the heat treatment processes given in group A. So you have your heat treatment processes and the kind of the effect that it will have on your properties. So you have to match them, right? So first is annealing, nitriding, mar tempering, normalizing. So first I'll just give you idea. You understand this is annealing. It is simply your slowly cooling in a furnace. While as nitriding is something in which you put your sample in a furnace at a certain temperature, and you put your mostly the nitride for nitriding the ammonia gas is used. So you are using ammonia gas, and this ammonia gas dissociates and gives you nitrogen or radicals of nitrogen. So that forms a layer on your sample, and that is a hard layer on your sample. So you do nitriding for that, where you are using a heat treatment with some external agent, which is here in the case of nitriding, ammonia gas. In mar tempering, you are converting the material to martensite first, and then you are also tempering it. That means you are first cooling it at a very faster rate and then converting it to martensite. And once the martensite transformation is started, then you temper it. Then you try to avoid the formation of your say for example brittle fractures on martensite, regions for your brittle fracture. For that you do tempering. Tempering is always done to relax or for stress relieving purposes, to avoid the formation of your high points of stresses that could lead to your failure in the material. And normalizing is heat treatment, but you have to you take the material above the austenite temperature, and then you cool it in a air cooling. So that is your normalizing. So these are processes. Now you have to say how it affects the property. Say for example annealing. What is the right option for annealing? What do you think among these properties will help you to attain the property? First, it says it refines the grain structure. Refinement of the grain structure only happens when you have a faster cooling rates, right? Because you're not giving the material enough time to grow. You are allowing the nucleation to take place, but you're not allowing the growth stage to pass. So refinement will not happen in annealing. So it will improve the hardness of the whole mass. No, the purpose of annealing is not to improve hardness. It increases surface hardness. It improves ductility. It is actually improves the ductility. So normally what happens when you go for annealing, you raise above the austenite temperature, then you cool it in a furnace, so that results in your for example increase in your ductility, because you can now have a material that is more that can sustain more strains, so it will improve its ductility. However, the strength of these annealed is lowered as compared to their material. So annealing is usually followed when you are doing a plastic deformation. So you are doing certain plastic deformations in your material, and after that it you need to relieve of the stresses and you want to increase the material's ductility. So you can go for a process of annealing. So option D is correct for annealing. So for nitriding, so you have options. What happens in nitriding? It is only the surface which is hardened, because you have a sample like this. Once the material is, once you are passing the ammonia gas, the surface is nitrided. So this surface becomes hard, while the core remains soft. So only the surface hardening takes place. So the for option B, we have nitriding. So you can match it with increasing the surface hardness, right? So now you can tell me what is for the next two. Ma tempering and normalizing. For Ma tempering, is option A or option B correct?
Option
B.
B.
Option
Option B, ma'am.
Option B, right? Because in Ma tempering, you are trying to convert your, you have to achieve a hardness in the whole structure. You want to achieve a Martensitic structure, but you have to also relieve it of its stresses. And then for normalizing, it is done for refinement of the grain. So you have to, okay, so I just wrote it wrong. So it is C. So for refinement of the grains, you can do normalizing. This is your
Ma'am,
C.
yeah, ma'am, I have a question in the heat treatment process, that, ma'am, when we go for normalizing and when we go for tempering, because I find these heat treatments somewhat confusing.
See,
Just my question is that when should we go for tempering, when we should go for normalizing?
tempering is only done when you have already some stresses built in the material and you have to just relieve them. So, for example, you want to achieve tempering is mostly done at a lower temperature also.
Yeah, at the
Also,
end of the heat treatment
yes,
process.
it is done at at lower temperatures, whereas for normalizing, you always have to get converted to an austenite form and then do the treatment. So you can say tempering is mostly a post-treatment method, whereas normalizing is your normal method which you have to utilize for refinement of the grains. But tempering is always followed by something before that, right? Either austenitizing or martensite transformation. So something needs to be done before you go for tempering. So tempering is only to correct the flaws that are produced because of your first treatment. So you are doing tempering, while normalizing is itself a complete treatment.
Okay, thank you.
So next question is, if the bulk modulus and shear modulus are 1 and 2 respectively, these are just values of your moduluses, 1 and 2 is given. So what is the value of Young's modulus of elasticity? So I think this is a relationship between about three moduluses. One is bulk modulus. This bulk modulus, see, moduluses normally are nothing but they are a ratio of your stresses to your strains, right? Nothing. This is a stress and this is your strain. So if it is a volume, like if it is a tensile stress, if it is a uniaxial stress and strain, then you call it as Young's modulus. If it is on a surface, along a surface in a shearing action, then it goes to a shear modulus. When it is a volumetric strain, when you are talking about strain which is in the volume of a material to your volumetric strain, so you are considering all three directions x, y, z for your stresses and strains. In your Young's modulus, you are only considering one direction for your tensile operations or for your strains. So you have three moduluses, and all three moduluses are actually related to one another, right? So there is one equation, I am not sure if it is covered, but this is a relationship between your Young's modulus. So this is your I'll write the equations. So this is E is equal to 2g 1 plus mu. You understand what is mu, because it is always possible when you are elongating a material, there is always some change in its another direction. For example, if you are elongated along x axis, there is some dimensional changes along y and z axis. So the dimensions along y and z are decreasing as you are increasing the dimension along x. based on your conservation. So you'll always have some Poisson's ratio for that. So Poisson's ratio is nothing but it gives you an idea how much elongation takes place in all the directions. It is a relationship between your longitudinal directional change in your dimension to the changes along your another two dimensions, which are y and z mostly. So this is your E is Young's modulus, G is your shear modulus, and you also have a relationship of your Young's modulus with your bulk modulus. So that is 3k. So you have three moduluses here and mu, which is the Poisson's ratio. All of them are related to one another. Young's modulus, shear modulus, bulk modulus, and this mu is your Poisson's ratio. So you have an overall relationship. If you uh, try to find a relationship between them, then you have a E is equal to, this is simple relationship to remember, 9 kg divided by 3k plus g. So this is a very simple equation that we remember, that if there is a product at the top and while there is a sum at the bottom. So this is your final relationship between your Young's modulus, so which is to be found in the question. So you have to find the value of Young's modulus. So you have to find the value of E, U, K is your bulk modulus, so that is given as 1. Your G, which is shear modulus, that is also given, which is G. So you just have to put the values. So you have 9 multiplied by 1 multiplied by 2, and that is divided by your 3. K is your again 1 and your G is your 2. This is plus, right? And just correct it. So what is the answer? Just have to put the values. This will be 18. This will be 3, 1 and 2. That is 5. 18 by 5. And that is equal to, so what is the right answer? 3 point?
3.6.
Okay, 3.6 is your answer then. Okay. So next question is about factor of safety. It says that factor of safety is given by formula: permissible stress to ultimate stress to permissible stress, shear stress to shear strain, tensile stress to shear strain. So normally when you are talking about a new material, when you understand that it has a certain ultimate tensile strength, so you know that it is a maximum stress that it can endure. So UTS is, you know, for a material, you know, yield stress, you know, ultimate tensile stress. So basically when you are using this material, you always operate the material below its ultimate tensile stress, right? So in order to have some factor of safety, in order to avoid any mishap, right? So it is always given, it is actually in terms of your stresses. It is not a property of your strain, but it is your property for stress, right? So your factor of safety is always given for a material. So you have to operate, you have to see how much factor of safety we should give for a material in order to operate it in a certain conditions when we know their ultimate tensile stresses, right? So the factor of safety is actually not about strain. So these options are wrong because it is about your stress, right? It is not about your strain. So factor of safety is actually given by ultimate tensile stress, which is your the maximum that it can endure, and the permissible. So how much you are allowing it to endure. So that is sigma allowed, or we can say sigma permissible. So this is the ratio of your factor of safety. So you can be given in your questions that if you have given an ultimate tensile stress and there is a factor of safety, say for example 10% or so, so you have to find what is allowable stress that the material can function at, right? So for this question, the right answer is this: the ultimate stress to permissible stress. Okay. Then we have another question which says Which of the following is correct order of cooling media for increasing the cooling rate? This we have discussed. So you just have to say the increasing cooling rate. The order should be like the slowest cooling rate and the fastest cooling rate. So we'll go from slow to fast. What is the sequence? Which is the right sequence?
Option B.
Option B, right. So air will have the slowest cooling while the water will be having the highest cooling, while oil has intermediate cooling, and fuel salt also has somewhat lower cooling rate as compared to your oil. Okay, so these are next question. So the next question is based on your amount of energy that is being stored. So you know that there is certain amount of energy that is stored in a material, certain potential energy that is stored when you are undergoing deformation or undergoing any transformation because of the tensile or stresses. So it is saying that when elongation in a rubber band is 3 centimeter, the stored energy in it is of magnitude E. What will be the energy stored when the elongation is 6 centimeter? So you have to you this is a straightforward question. You should know that there is a stored energy in a material because of the stresses. So obviously when you are having a higher elongation, you are creating larger strains, and large strains will result in large stresses in the material. So you will have a higher stored energy in the material. So right. So is it E? It cannot be same as E because you have elongated it from 3 centimeter to 6 centimeter. So logically, E is not the right option. Now you have to see what is the parameter that influences it. So do you know what is the formula for your stored potential energy?
Half into sigma into
Yes, it is something half of some constant I'm taking here. So this is your elongation. So it has a elongation. The relationship between your stored energy and your elongation is square, right? It is a parabolic function. So you have to say if you have a two values, so you have u1 and u2 stored energy at when you have 3 centimeter, when you have 6 centimeter. So you have 3 cross 3, then you have 6 cross 6, right? So you have 1 by 2 cross 1 by 2, so that will be 1 by 4. Okay, so you have to say what will be the energy when it is u2. So you have to find for u2 stored energy for case second. So you have 4 times u1. So you have this relationship. Obviously the energy stored will be higher, so it is 4 times the energy than it was at in case 1. Okay, so I think that is all for today. So we have done some questions related to stress strain curves and some temperature, some heat treatment related questions. So if you have any question.
Ma'am, I have a question and a request. Please reply the questions which are being put on the dashboard by the student.
I am not, you're not audible.
We have put some questions on the dashboard.
You have put some questions where?
On the madam dashboard.
Okay, in the discussion forum. Okay.
Yeah, sir. Would you please reply these questions, ma'am? They are pending for long, ma'am.
Yes, actually, the discussion forum is not handled by me, so it is handled by the one who uploads your questions for this year
Okay.
assignments. I'll convey it to him, so maybe he'll reply.
Madam, my question is that we have defined these temperature ranges like ACM, A1, A3 lines, ma'am.
Mm-hmm.
Madam, how these lines get their name? ACM, A1, A3. What is the logic behind naming them 1, 3, and CM?
CM is nothing but it is the transformation after cement. Like CM is cementite transformation. A1 is the this. I don't think there is any background, or I am
Okay.
not sure.
It is just an arbitrary number.
Yes, yes, I'm not. I am not sure if
Okay.
there is any specific reason, but yeah.
Okay. Thank
Mm.
you.
Is there any other question? I think that is all for today then. I will convey your questions about the discussion forum. Then maybe you can have a reply.
Thank you, ma'am.
Okay.